You went bungee jumping in Queenstown. Oh, to celebrate your perfect score on the mechanics exam. Well done. Congratulations. The combined mass of you and the equipment is 80 kgs. So we're given a mass, M. The jump pad is 100 meters off the ground. So ground level, 100 meters. However, you will only fall to 60 meters off of the ground before the cord stretches a further 10 meters. So at 60 meters, so you jump, you will then stretch, well, you won't stretch, the cord will stretch a further 10 meters. Right, so that initial distance you fall is 40 meters, and then an extra 10 meters as the bungee cord stretches downwards, and then of course you'll bounce back up and start to oscillate a bit. So that's the context. Question A, calculate your gravitational potential energy relative to the point where the cord begins to stretch. So often we take gravitational potential energy relative to the ground, right, the ground level. However, it's just relative to some point. And in this case, we're taking it relative to this point right here, which is after a change in height of 40 meters. So your gravitational potential energy, mass times gravity times change in height, right? Notice how it's change in height and not like absolute height from the ground. So substituting in our known values, you have a mass of 80 kgs, or you and the equipment, excuse me, gravity 9.8, and change in height would be 40 meters. And again, that's to the point where the cord begins to stretch. So now we can calculate that. So 80 times 9.8 times 40 gives us 31,360. And units for potential energy or energy would be joules. And to round our answer sensibly, we'd look at the information we're given. So 80 kgs, that is to one significant figure. So we'll round our answer also to one significant figure. But I wrote our unrounded answer there just in case we need it in a further calculation. Okay, so again, what this is how much potential energy you have from the launch pad relative to the point where the cord starts to stretch, so to that red dot, from the blue dot to the red dot. Of course, if we calculated it, the height as to the ground level, you'd have much more potential energy. Okay, now question B, you jump, surprise, bungee jump, and you fall to 60 meters off of the ground. So you fall to this red point. State the kinetic energy you have at this point. So we started with gravitational potential energy, and as you fall, you accelerate, right? And that converts into kinetic energy. And if we ignore air resistance, right, which we kind of can in this situation because your surface area is quite small and you won't be traveling ridiculously fast, all of that potential energy will convert to kinetic energy. So we would say, by conservation of energy, EK will equal the potential energy, which is 31,360 joules at that point. So that's how much kinetic energy you'll have at that red dot, so after falling 40 meters. And question C is now calculate your velocity at this point. So we know our kinetic energy, and we know kinetic energy is a measure of how fast you're going, squared times your mass, divided by 2, right? EK equals half mv squared. And so we know how much kinetic energy you have, and we know your mass, so we can solve for your speed. So substituting in the known values, notice I'm using the unrounded value here for kinetic energy, equals half times mass, which was 80, times speed squared, which is what we're looking for. So half times 80, that's 40. I'll divide both sides by 40. And so we're left with v squared equals 31,360 divided by 40, which is 784. Now, is that how fast you're going? No, right? Last step, we solved for speed squared, so we need to now square root. And 784 meters per second would be ridiculously fast. So we can go shift square root, shift answer to get 28 meters per second. And what's that in kilometers per hour? That is almost exactly 100 kilometers per hour. So pretty fast, but much more reasonable than 784 meters per second. So after traveling 40 meters, you have gained a speed of 28 meters per second. Now, part D, you fall a further 10 meters as the cord stretches. State the elastic potential energy you have. Right, so you've gained all that speed, now you're at the red dot. However, the cord is now under tension, and as you fall this last 10 meters, the cord is resisting you, so it's trying to pull you back up. And in doing so, you have converted your kinetic energy into elastic potential energy, right, of the cord. So think of like a slingshot. When you pull it back, it's got stored energy, then you let go and it can fire, ammunition. In this case, you are pulling back on the slingshot, right, with your mass and your speed. So the elastic potential energy, I guess instead of elastic potential energy of the cord, I'll fix that in the final question, will be the same as how much kinetic energy you have, which happens to be the same as how much gravitational potential energy you have. So again, by conservation of energy, elastic potential energy will equal the kinetic energy that went into stretching the spring, which is also 31,360 joules, right, or 30,000 to one significant figure. Part E, calculate the spring constant of the cord. So spring constant is often denoted by K, and it tells us how much force is required to stretch a spring or a rope by a certain distance. So in your formula sheet, you'll have seen F equals negative kx, so that's Hooke's law. And you'll actually use that in class to investigate different spring constants by changing mass, which changes the force, measuring the distance, and you can find the gradient, which is the spring constant, K. But if we rearrange for K, we'll see that it's force over distance, so it has units, newtons per meter. So it's how many newtons of force do you require to stretch a spring 1 meter? Right, that's what it means. But back to the question, what do we know? Well, we have your mass, not very useful though. Sorry. We know that the spring stretches 10 meters. Okay, so that's its displacement, 10. So we label that as x. X just means distance or displacement from like an unstretched state, from its equilibrium. We actually worked out the elastic potential energy. And looking at your formula sheet, we know that the elastic potential energy in a spring is equal to half times the spring constant times how far it's stretched from equilibrium squared. Right? And we know potential energy, and we also know the distance, so we can solve for K. So let's substitute in the values. For potential energy goes 31,360. In for K goes, well, nothing, because that's what we're solving for. And in for X will go 10 meters. Already in SI units, but we need to square it. So what does that give us? 10 squared is 100. And 100 times a half would be 50. So the right hand simplifies to 50k. We can then divide both sides by 50, which leaves k equals 31,360 divided by 50, 627.2, which to one significant figure would be 600 newtons per meter. Right, so it requires 600 newtons of force to stretch the cord by 1 meter. And that's solving for the spring constant. Alright, and finally, on your next jump, because of course you need to go more than once. I mean, you did get a perfect score on your mechanics exam, so it is worth celebrating. On your next jump, you use a cord with a lower spring constant. Explain the effect this will have on your jump. So the rope is, weak is not the right word, but it requires less force to go the same distance. Or for the same force, it will stretch a further distance. So let's try put that into words. If K decreases, it will stretch further if the same force is applied. So what does this mean for your jump? Well, you aren't changing your mass or anything, so you will apply the same force. However, instead of only stretching 10 meters, we would expect it to stretch perhaps 15 meters, right? It'll stretch further because the spring constant is less. So if K decreases, it'll stretch further if the same force is applied. Yep, I think that's all we need for that one. Cool, and what would happen if the spring constant was greater? Right, if the spring was greater or stiffer, your 10 meters might turn into only 5 meters, right? And that could be quite uncomfortable. So the people running the bungee jump facility do need to pick, a cord with the right specifications so that you don't get your feet don't get ripped off, essentially, or it's not too loose that you fall and crash into the ground. Yeah, both of those options are not very good. However, you survived and we got some physics out of it. See you next time.